Thank you for a very kind introduction. I am Xiu Gui from East China Normal University, Shanghai. I will present our paper, an efficient dense depth map estimation algorithm using direct stereo matching for ultra-wide-angle images. Ultra-wide-angle lenses capture larger views of the surrounding environment and expect to benefit many applications, such as augmented reality and robotics. Here are three ultra-wide-angle images. Estimating the dense depth map from the ultra-wide-angle image is a challenging problem. First, the images have severe geometric distortion, so many standard stereo matching algorithms need to rectify the image, which needs to loosen the view coverage. Second, 3D reconstruction algorithms only utilize the sparse features of the wide-angle images. The rich information contained in the image was omitted. A few stereo matching methods are designed for ultra-wide-angle images, but they all have limitations. For images captured by a pinhole camera, there are many stereo matching methods with promising results. One can rectify the wide-angle images and then apply those methods to generate dense depth maps. However, this will generate noticeable noise in the resulting depth map. As shown at the bottom of this slide, the depth map for rectified view has noisy values on the boundary of the image. There are also some direct stereo matching methods, such as plane sweeping and variational fisheye stereo. While plane sweeping tends to select depth value for each pixel in the predefined plane hypothesis, this may miss the correct depth values. The predefined possible planes are limited, so the number of candidate planes is infinite. Variational fisheye stereo can only apply to ultra-wide-angle stereo pairs with small displacements. We present a new efficient patch-based stereo matching algorithm for the ultra-wide-angle lens. Our algorithm can directly apply to ultra-wide-angle images and generate high-quality dense depth maps. Patch matching stereo allows finding accurate depth values for each pixel in an infinite space with a random search strategy, which avoids missing correct planes. The proposed algorithm deals with stereo pairs with an arbitrary baseline, which allows handling the rapid camera movement. Besides, the proposed method can work with any camera projection model as long as it has a closed-form inverse. Now I will explain the details of the proposed algorithm. Depth clues of the pixel play a crucial role in 3D reconstruction task. The depth shows the distance between the corresponding scene point and the camera. We tend to find the accurate depth value for each pixel. For this end, we will find the best matching patch in two views. We first assign the plane to each pixel, which relates to the pixel's depth. The pixel can be mapped to different places in the other view with various plane assignments. The best matching patch means the correct plane for the pixel. So first, I will explain how to locate corresponding patches in two ultra-wide-angle images. Then we will evaluate the image similarity between those two patches, and how to search for the best matching patch in the other view. We use homography to perform panel mapping for each pixel to locate the corresponding patches. We define the scene point of each pixel by the plane it locates, and we define the plane by the depth and the plane normal. When a pixel is assigned with a plane, the pixel is first back projected to the scene with the depth and the plane normal. For a back projected pixel in the ultra-wide-angle image to the scene, we choose to model ultra-wide-angle lenses with the double sphere camera model. In the bottom right corner of this slide, you can see that in the double sphere camera model, a point in the world space is projected onto two unit spheres consecutively. With a double sphere camera model, we can back project a pixel in the ultra-wide-angle image to its corresponding viewing ray. We are then using the depth value to locate the scene point in its viewing ray. And the plane normal defines the plane's orientation. As shown in the bottom right figure, we can map this scene point to the other view using the projection function of the double sphere camera model, so we can locate the corresponding patches in the other view. We compute negative zero mean normalized cross correlation over the corresponding patches to evaluate image similarity. First, we assign a random depth value and a plane normal for each pixel. Then we apply the patch match stereo to search for the correct planes for each pixel. After random initialization from the probability point of view, some pixels must have plane parameters close to the correct ones. We can propagate those guesses to its neighboring pixels. For the local pixels inside the patch are likely to lie on the same plane. We traverse the given image in a row-wise order and optimize the image iteratively. For each pixel, we examine whether the plane parameters for neighbor pixels are better choice for the given pixel in the spatial propagation. Then we will show our experimental results using TUM Visual Initial dataset that contains an ultra-wide-angle camera stereo pair. The figure shows the depth maps generated from one camera from an ultra-wide-angle stereo pair. We use random initialization for the first image, and then the previous depth map will be used as the initial depth guess for the following image. If we generate both depth maps for the stereo pair, we can use the depth results of one image as the initial guess for the other. The video shows that our algorithm generates clear depth maps for the ultra-wide-angle image. Here we present the point clouds generated by the depth maps. As shown in the figure, the highlighted part has a clear structure. The top row is a rectangular stair, and the bottom is a bench. Moreover, our algorithm can work for any camera projection model as long as it has a closed form inverse. Here we present the results by applying the unified camera model. The depth maps shown in the previous slides are generated with the double sphere camera model. It means our algorithm can generate high-quality depth maps under the unified camera model. Here we show more experimental results. The left figure shows the evaluation of computational time under various matching window sizes. The figure shows 3 camera models, and the pinhole means we first rectify the ultra-wide-angle images. The computational time is influenced by the projection function of the camera model. Thus, the double sphere camera model takes a longer time. In the right figure, we evaluate the matching cost in terms of the number of iterations. A larger matching window has a lower matching cost while taking more computational time. We also compare our algorithm with the other three methods. The first one is patch-match stereo under rectified ultra-wide-angle images. The other two methods are directly applied to ultra-wide-angle images. Plane sweeping is a widely used stereo matching method both for perspective images and ultra-wide-angle images. Variational fisheye stereo searches for the correspondence along the epipolar curve. Here is a group of the comparison results. Here are some comparisons with those methods. The rectified images under the pinhole camera model exhibits clear noises near image boundaries. Plane sweeping generates inaccurate depth values in the resulting depth maps. VFS generates depth maps with fewer noise, but the objects near the boundary are blended with the background. Our algorithm generates high-quality depth maps with clear and sharp object boundaries. Due to a large matching window size, the objects may expand slightly along their boundaries. We also perform quantitative comparison in terms of computational performance and matching accuracy. In the TUM-VI dataset, we evaluate the depth error and matching cost for those methods, and compare the resulting depth maps with LiDAR scans in the Oxford robot car dataset. As shown in this table, our algorithm outperforms other algorithms in terms of efficiency and accuracy. Here we present the comparison with LiDAR scans. We show the visualization of depth error compared with LiDAR. The left figure is the depth map generated by our method. The figure next to it is the LiDAR scans, and the other figure shows the depth error. The depth error increased in the same points far away from the camera. We observe that our algorithm's depth map is close to the LiDAR scan. This paper proposes an efficient dense depth map estimation algorithm that can be directly performed for ultra-wide-angle image. Our algorithm applies patch-match stereo to ultra-wide-angle images using the double-sphere camera model, and generates high-quality depth maps with clear object boundaries. However, our work has a few limitations. There are false matches for textureless or shining surfaces due to the insufficient local evidence. This comes to the end of my talk. Thank you for your attention.